Welcome back to the PLC Professor's Development Lab and Workshop. In this lecture, in this discussion, lab project, we're going to do shift registers. Shift registers are not the most popular way of accomplishing what you're going to accomplish with a shift register. There are more straightforward ways to do it. However, as I have explained before, if you're going to have to do maintenance on systems, troubleshoot systems, then you have to be prepared to understand any method that the person used that wrote the program to write the program. And that would include shift registers. Shift registers, simply put, is a length of bits. It could be a part of a word, multiple words. Just picture a number of bits in series. And someplace along that line you're going to inject a specific value of 0 or 1 and then shift the whole thing either to the left or shift it to the right. So there's a bit shift left and a bit shift right. There's a source, there's a bit address, meaning where does a bit come from that you inject, and then there's a length. So you could take a 32-bit word, a double integer, and you could shift just a section of the bits anywhere between 0 and 31. So let's get after this. Shift registers. Actually, there's no such thing as a shift register. A register is kind of a universal term for a variable or a pointer or a memory location. And memory locations for the stuff that we're working with are the atomic data types, Boolean, single integer, integer, double integer, real. And then you've got unsigned integer, unsigned single integer, unsigned double integer, etc., etc. So a register is just a word in memory. And if you wanted to, you could even call out X number of bits in a word as a register if that's your specific target. Now in this case, when you hear the term shift registers, you're entering into a discussion of shifting the values in the register to the left or to the right. So we have two instructions that we're going to be working with: bit shift left and bit shift right. And to start out, we're gonna work with a graphic that I created here. It's kind of crude. It's not a perfect example, but it'll do the job. So we've got a tube with ping pong balls in it. And notice that I show integer 0 through 15, double integer 0 through 31. It doesn't have to be an integer or a double integer. It could be a single integer. It could be a long integer. It's just a register. It's just a variable. And in this case, we're showing 0 through 31, but it could be 0 through 15. And what we want to do is we want to take and push on these ping pong balls at one end. If we push on the right end, we're pushing to the left. We're shifting to the left. But we can also push on the other end and shift to the right. But the left one is the easiest one to start out with, so we'll do that. Now, we have something called a bit address for a shift register. And notice that we've got our ping pong ball locations or designations 0 through 31. Notice that the ping pong ball that's sitting in front of the actuator is not part of the shift register. It's not part of the source. That's the loading point. So whatever we have at the bit address is staged, ready to be pushed into position 0. And of course, we know that if you push that white ping pong ball out of the bit address into position 0, it's going to move 0 to 1, 1 to 2, 2 to 3, 3 to 4, and so on down the line. And theoretically, there'll be no delay in motion. They'll all shift together. And so whatever ping pong ball, which is a white one, at the bit address After we've executed this bit shift to the left, that white ping pong ball is going to be in position 0. So you look at your 32 ping pong balls there, 0 through 31. Then, of course, you got your bit address. A 0 is a 0. So if we push a white ping pong ball into that tube, of course, we're going to pop one out the other end. But you still got 32 white ping pong balls in that tube. So the execution is a matter of, if in this case I'm showing a piston with a pusher on it that's going to push that white ping pong ball that's supplied by the bit address into position 0 when it executes. Now, what I've got displayed there to pick between a white and a black, a 0 and a 1, you see a little deflector that can rotate and drop a black one down in the load position or a white one down in the load position. And that's based on the state of your bit address. So in other words, the bit address, it's Boolean, it can be 0 or 1. And whatever is staged at the beginning of the ping pong ball tube there, when you execute, that's what's going to be pushed into the load position. Now, maybe a little bit better mechanical illustration would be a side-by-side magazine. Now, the orange dashed line is the tube that the ping pong balls get pushed along. So you have a magazine, sliding magazine, that, as you see in the left, the white ping pong balls are staged at the opening, and that center line is the direction of travel down the tube. Or you can slide your magazine over to the right, and now you've got a 1 staged. So you slide this back and forth based on flipping the switch. So we're going to use a input, a actual embedded input, 0 or 1 or 2. We're just going to use an input, and that's going to be the bit address. So if we turn on input 0, then we've got a 1 staged. If we turn it off, then we've got a 0 staged. Here I have in the top image there, you have a white ping pong ball that's staged at the shift register. Now remember that the stage position is not part of the 32-bit word. When we execute this shift, it pushes all 32 ping pong balls plus the one from the bit address. So you're actually pushing, if you like, 33 ping pong balls. And one's going to pop out the other end. So this is the basic idea of a bit shift left. We can load a white one or we can load a black one and push it to the left. And then of course, when you retract the execution. So we have 2 memory locations here that we're turning on and off. Input 1 is the bit address, and then the piston or the cylinder, that is the execution. So when the rung goes true, it executes, and when the rung goes false, it retracts, and whatever position input 1 is in, that's what pops in next. Now if you go back to this diagram, as long as you're not executing the shift register, you can flip the bit address back and forth 0 and 1. And you're going to stage a 0, stage a 1, stage a 0, stage a 1. This discussion applies to anything RS Logix 500, 5000, Studio 5000, Micro800, Connected Components Workbench. This discussion applies to any use of bit shift instructions, whether it's bit shift to the left or bit shift to the right. Right now we're showing you bit shift left. And there are a number of elements that you need to cement in your mind looking at this illustration. The position at the face of the piston that's pushing the ping pong ball to the left, that is the bit address. It is not part of the shift register It is not an element of any array 0.0-31. Now remember that all that you need is a word in memory that you can access with a bit shift instruction. It doesn't have to be an array, it doesn't have to be a double integer, it doesn't have to be an integer. I'm showing 0 through 31, which would be a double integer. So any array is an array of double integers. How many? That's determined by the dimension. When you specify, or when you define the tag, the variable, you specify the data type and the dimension. The fact that we see brackets with a 0 in it, that implies that it is the first element of an array of more than one double integers. Okay, so the register that we're going to shift the bits in is any array element 0.0 through 31. So you can see the ping pong ball that's in the yellow square, that is not a memory location that's part of that register. It is input 01. So basically we are staging the state of input 01 in between the face of that piston and the first bit or least significant bit in the word. Okay, so we have a register address, a variable address in which we're going to shift the bits to the left. Then we have a bit address, which the state of that bit determines when you execute the instruction whether you're inserting a 0 or a 1 into the least significant bit, bit 0 of that word. And then we also have an execute. Now, the execute typically is an input to the instruction. And because you could have an unconditional rung, in other words, no conditions or permissives between the beginning of the rung and the input, the execute input on the instruction, it is not assigned a permanent address. What I have is I show input 0 as a switch, but it's a bit in memory, and when that bit goes true, or when that bit goes on, then the instruction is going to execute and it's going to push whatever's in the bit address into position 0 and push all the bits in front of it to the left, and then whatever is the last bit in your register, in this case it was bit 31, whatever's in there gets popped out into nowhere. Now in this case, we started out with all zeros, all white ping pong balls 0 through 31. And we have a white ping pong ball, a 0, that's the state of input 1, it's 0. So when we execute by toggling input 0, we're pushing a 0 into bit 0 position. So when you look at the state of those 32 bits from the top diagram to the bottom diagram, they don't change because you just pushed in another 0. And of course, keep in mind that any number of those ping pong balls, 0 through 31, could have been black, which means you would have seen something move because you would have seen the black one shift one bit position to the left. This is more or less the logic that we had at the beginning of M24, bit shifting left and right lab project. Now, if you're accustomed to the way I do things, I don't always follow the manual. I try to make sure I cover anything that's in the manual, but if I can show it in a different way that extends or enhances your learning experience, I'm going to do that. Now, in this case, we pretty much have stuck to what was in the manual, other than, notice for my bit address, I have IN01, and for my unload, I have OUT00. I also, for my permissive, have input 0 or IN00. because if you look over to the left, you'll see that I have buffer input and buffer output program files. So I have used the template that you created back in Lab Project M9 in Volume 1, the first semester. I created a template in that manual and had you do the same, where you buffered all of the I/O available on the simulator. So I have IN00 through IN27, and I have OUT00 through OUT19. And I do that because buffering your I/O is always good practice, but it makes for much cleaner programming, because instead of having underscore IO EM underscore DI underscore 00, I just type in IN00. Just makes it easier. Now, something I want to point out to you. I have the database exposed here. So the source is sequence bits. Now, in the manual it was sequence, but because I have a program file called sequence, it didn't like me naming this sequence. So I just called it sequence bits. And you see I have it exposed here, so we have an array of 100 Booleans. See the dimension over here? 100. So sequence bits is an array of 100 Boolean data types. And since we're doing a length of 8 for this bit shift left instruction, and you're thinking, this is going to vary a little bit from RS Logic's 5500, 5000, and you'll see in a minute why. So we're only concerned with the first 8 bits. Now, one thing I noticed is if I go in and check sequence bits element 1, notice that it now says true for sequence bit for the source. And if I toggle the second one on, it still stays true. If I toggle off element 1, it goes back to false. So I wouldn't pay too much attention to this when you're analyzing your code. Now, one thing that is important here is the done. This rung will go true when you're done executing the bit shift left. It doesn't mean that there was a specific value at any of the registers. That is determined by the unload. So because we have a length of 8, then we're going to unload whatever's in the 8th position. So, and we'll go through and we'll do that down here. So let's start out by turning on, no, let's just toggle input 0. And you see that the done bit goes on until I untoggle. Okay, but you see nothing changed. If you shift 8 zeros, you still got 8 zeros. So, and by the way, I'll just do this for grins. I can check any bit. And then when I do an execution, keep your eye on bit 4 and bit 5. When I do the execution, see, it moves from 4 to 5. So when you're shifting these bits, these data types, it really doesn't matter how it became a 1 or a 0. That's up to you. So you could have logic that puts in values, in other words, true if on such and such, energize output, or direct coil, and you could address a direct coil to sequence bits 1, 2, 3, 4, 5 through 100. So you can put the 1 values in there any way you like. So we'll leave that one right there. No, I'm going to uncheck it because it wasn't part of the lab. Okay, so we're all clear right now. So if I just keep turning on and off input 0, you're not going to see anything change, but it's going to be shifting. So instead, let's turn on input 1 and then back off. If I turn it on and back off, nothing happens. I have to leave it on if I want to stage a 1 at the beginning of the shift register, so you don't see anything show up here. Because remember that the bit address right here, input 1, is not part of the source, the sequence of bits. However, if I execute it now, turn on 0 and back off. Now you see it sets the first bit at a logical value of 1. Now remember, there's no physical value. Logical value implies the state of the bit in memory. Physical value would be where you actually had I/O. There is a physical value for I/O, but not for straight up bits in memory. Okay, I'm going to turn off input 1, and then I'm going to turn on 0. So watch the value of bit 1 and bit 2. I'm going to toggle 0 on and off, and you see it moved. It shifted. Now, it's shifting down on the page, but it's shifting from the least significant bit towards the most significant bits. Now that was one shift from bit 1 to bit 2. And it pushed a new 0 into bit 1. Of course you can't see that because you can't see it change from 0 to 0. There's nothing to see. So I'm going to toggle bit 0 on, and you can see it moves down to 3, off, on, off, on, off, on. And now you can see it's moved down to 6. Now bit 7 is the end of the length. Well, it's not. It's bit 7 is the second to the last. So I'm going to go one more time, and you see that moves it to 7. Okay? So we're talking about a length of 8, even though we have 100 Boolean data types all lined up in an array. We're only working with a length of 8. So I'm going to toggle 0 off. Run goes false. I'm going to toggle it on one more time. Okay, and it goes to the last position, 8, 1 through 8. So when it gets to the length, it's still there. Now I'm going to go one more time and watch 8 and 9. It left 8, but it did not show up at 9. But notice that the unload now is true. See, down here, output 0 went on. So that's the unload position, whatever memory location you put in here. Now let's say that you wanted to recirculate the state of bits. You could always unload this and then get it back into the bit address. In other words, remember, this is a bit shift left instruction, and you've got these variables to work with. You could do a source offset. Maybe later on we'll play with that, maybe we won't. What I wanted you to notice though, if you're familiar with RS Logics, you would have unloaded when it shifted from 8 to 9, but 9 would have been on. And as you continued to shift, you would see the bits go all the way to the end of whatever length of bits you had specified. And I don't mean the length. It unloads at the length. So if you were using a 32-bit word, a double integer in RS Logics, and you were doing a length of 8, when it went from 8 to 9, it would have moved from 8 to 9. 9 would be a 1, and then shift again, 10, 11, and it would keep right on shifting until you got up to 31. Then when you shifted one more time, it would bump it out into the bottomless bit basket. So this is one departure from RS Logics with Connected Components Workbench. Actually, I think I like this better, because technically those bits that kept on shifting out to the end of the boundary of your length really were useless. Okay, I made a little change, actually just one change, and you can't do this while you're running. So you can either do run mode change if you have the developer's edition that supports run mode change, or you just save, disconnect, go offline and make the change. I changed the source offset to 4. I had 0 in there before, which means that sequence bits element 1 was the first element of the array to be shifted, or the register to be shifted. I put in a source offset of 4, which means now it's going to be offset by 4. Now you might be thinking, well, does that mean that it's going to be 4? I'm moving from 1 to 4. Well, that's not really an offset of 4. Moving 1, 2, 3. Okay, we'll do it this way. 1, 2, 3, 4. So that would be sequence bits. The 5th element. Now we are running, so let's just toss a 1 in there. So we turn on our true, or our bit address here. It's true. We toggle 0 on and off. Notice that the first insert is at the 5th element, so it's an offset of 4. Now, we have 100 Booleans here. So technically, you could start anywhere in that group. Just for grins, I'm going to do something that shouldn't work to see how it behaves, and I'll be right back. What I did was I increased the source offset to 98. Now we have 100 elements. So if our source offset is 98, then we're going to expect the first inserted 1 to appear at that location. So let's, first of all, we'll just scroll down, whoops, to the bottom. So there's 98 is right there. So let's turn on input 1, that's our bit address, and then let's toggle 0 on and off once. Now, I was expecting to get an error. So if I go back up here and look, and let's execute it again. Oh, I see what happens. The done bit doesn't come on. Now we got an error ID. Okay, that's what I was expecting. What that error ID is, I have no idea, but I can tell you this, that we exceeded the boundary of the source. The source is 100 Boolean data types. And we put in an offset of 98, and of course nothing appears all the way down there. You can see that nothing, we did not insert a 1 anywhere into this area. Instead, it just didn't complete and we got an error. Okay, I was just curious what would happen if we did that. Those are the kind of things that the space cadets, you know, when they're doing the course and they're doing stuff, they say, well, what would happen if you stood on your left foot, put your arm around behind your head and held on to your right earlobe and jumped 3 jumps on one foot and then switch to the other for 2.5 jumps? What would happen? Okay, you know, that kind of crazy stuff. So now you know. Okay, I changed the source offset back to 0, so everything is reset as it is in the manual. I also put in my poor man's HMI. In other words, I've got sequence. Oh, by the way, you see I shortened the name on the source from sequence bits to something more abbreviated, otherwise it takes up too much space horizontally. So I did make that modification. And I also created a tag called nada, which is just a bit memory. And if this rung is true and it turns on nada, nada doesn't do anything. So it's just a placeholder. So I could put in a rung to show these 8 bits. So now I'm going to toggle on input 1 and then input 0. And you see that sequence bits 1 comes on. And I'll do it one more time, so we've got 2 of them on, sequence bits 1 and 2. Turn that back off, turn input 1 off, and now start stepping them through. So you see 3 went to 4 and 2 went to 3, and one went to 2. The thing is, you can't tell the difference between 0 and a new 0. So right now, in the course of doing these 4 bits, we inserted 2 on values and 2 off values. And there's no way to tell the difference between this rung of logic with these 2 instructions true, because you executed the bit shift left and you just went in and toggled them on, which you could have done. So I can go right here, toggle Boolean value, toggle Boolean value. Now what's the difference between that and whatever brought about, and I have to bring this back up. And then we shifted and shifted again. You see, I'm saying, however the bits get changed, the bits don't know. Those 8 bits don't have any idea how they got in the state they're in, which gives you a lot of latitude in thinking up real clever ways to use bit shift left, bit shift right instructions. Now I told you that there are other ways to do it where you can avoid the BSL and BSR. So the whole reason we're doing all this is because as someone who has to support automation out in the field, you have to be able to interpret and analyze everyone's logic and why they use BSL and BSR. That was their business, it worked, somebody signed off on it, it was commissioned, the runoff was good, and the machine's been operating, and now there's something wrong and you got to figure it out. That's why we're doing these instructions. Now if I keep toggling across the screen, eventually they get down to the end, and now I've got 7 and 8. So now watch the output down here. Output 0 right here, and we're going to toggle it one more time. And notice that 7 moved to 8 and 8 went off into the bit zone. But notice output 0 is on. Now if I toggle it one more time, it's going to move 8 out, but it's going to turn on output 0. So that if you want to say the last bit in the sequence, it doesn't reside here and here. In other words, it goes from here to here. Now, if it's a 0, this is going to say false. So if I do this one more time, I'm moving the 0, or the off, of sequence bits 8 to output 0. See, and it went false. So when you unload, it's there when it leaves your length. And then one more execution, and it takes the last element in the length and puts it in the unload position, which in this case was 0, so it says false. If I don't explain where to get the manuals and what they are in the videos, then I get dozens of emails asking where to get the manuals. This RS Logix 500 manual is really the culmination of quite a few years of MicroStarter Lite, MicroStarter, and RS Logix 500. RS Logix 500 will program all SLC 500s and all MicroLogix. MicroStarter and MicroStarter Lite will only program MicroLogix. The starter is not free. It's about $200. Starter Lite is free, but Starter Lite will only program the MicroLogix 1000 and 1100. Then for 5000, RS Logix 5000, Studio 5000, we have 3 volumes, Fundamental Programming, Programming Examples, which is really one manual broken into 2 volumes, and then the Advanced Discussions and Lab Projects. The software for this hardware that this programs, the least expensive license is about $1,000, just under $1,000. And the hardware is also relatively expensive. You can find used compact Logix with some I/O for in the $500 range, but the minimum license is going to be just under $1,000. For Connected Components Workbench with the Micro800, the software is free, so you don't have to buy any hardware. Starting with version 12 of CCW, they included a simulator that works really well, and we really emphasize the simulator in all of our manuals. We also have a separate volume for PanelView 800 and PowerFlex 525. The PanelView 800 projects in this third volume, they are integrated into the actual lab projects in Part 1 and Part 2. So after you do a lab project in Part 1 or Part 2, for the most part, most of the labs, you can then immediately go to the third volume and do a panel view lab that integrates with the project you did in Part 1 and or Part 2. Not all the projects in Part 1 and 2 have PanelView 800 projects that complement them. And then for PowerFlex 525, we have both projects using controllers, and also we show you how to hardwire your PowerFlex 525s with push buttons and lights. For the volumes that you see, the lecture discussions are complete and available for all but the Part 2 of the CCW manual. Most of them are complete and currently going on YouTube free, and we don't have any done yet for the third volume for the PanelView 800 or PowerFlex 525. But keep in mind, you don't need to subscribe to the videos to do the projects in these manuals. The videos are for people that would like a little bit more explanation and tutoring. Have a nice day.